rational functions. My suspicion is most of you guys wouldn't have gotten to this in your Algebra 2 class, so we'll try to be pretty careful and go kind of slow through this, but that's the plan for today. We want to start by defining what we mean by a rational function. So we say that a rational function, which I'm going to denote as r of x, can be written in the form r of x equals some p of x over q of x, where p and q are both polynomials, and q is non-zero. So these rational functions are just built out of polynomials. It's a new function defined by the division of one polynomial by another polynomial. So today we're going to talk about some key features for those rational functions. So we're going to talk about these 6 key features today. Talk about domains, discontinuities, x-intercepts, y-intercepts, horizontal or slant asymptotes, and then end behaviors. So that's our agenda for today. Horizontal asymptote and slant asymptote. So to find the domain, we're going to set the unreduced denominator equal to 0 and solve. The solutions, those solutions are the x's that are not in the domain. So we're going to look at 2 examples here. So the first example, y equals x plus 4 over 2x minus 1, we'll start by setting that denominator equal to 0 and solving. Now, 2x minus 1, that's a really equal to 0 is a really easy equation to solve, right? That's just a linear equation. We'll add 1 to both sides and divide by 2 to get 1/2. So our domain should be then everything except x equals 1/2. Now we're not going to write it in words, we're going to write it using interval notation. So if we have everything except for 1/2, we need everything before 1/2 and everything after 1/2. So the numbers before 1/2 are going to start at negative infinity and then go up to 1/2, and I'm going to use a parenthesis on the 1/2 to indicate that we're not including 1/2. And the numbers after 1/2 are going to start at 1/2. Again, I'm going to use a parenthesis to indicate we're not including 1/2, and go on all the way to positive infinity. I know, it's okay. So that would be like the way we'd write our domain. Does everybody feel okay there? Is that... Nope, nothing to do with it for domains. For example B, here we have 3 minus x over x cubed minus 4x. So again, we're going to set that denominator equal to 0 and solve. What kind of an equation do we have here, though? Okay, or more generally, a polynomial, right? If I'm going to solve a polynomial, what's my technique I need to use? Factoring. Yeah, so if we go back to the last chapter, we're probably looking at having to use that factoring tree again, right? So if you run into a polynomial, it's probably going to be factorable. Probably going to land on this factoring tree would be the method that I would use to factor it. So that doesn't go away. So if I look here at x cubed minus 4x, according to the factoring flow chart, there we have the first thing we look for is the greatest common factor. Do you see anything common between x cubed and 4x? X, very good. So if I factor that out, I have x squared minus 4. That leaves me with a 2-term polynomial there, the x squared minus 4. If I go down the 2-term branch of my factoring flow chart, I see the first thing I check for is a difference of 2 squares. Is that a difference of 2 squares? Yes. How does it factor then? X plus 2, x minus 2. That's correct. Now, each of the factors is linear. They're all degree 1 factors, so I know I'm done. So if I set each piece equal to 0, I can solve, and I get x equals 0, x equals negative 2, and x equals positive 2. Everybody okay there? So when I go to write my domain, I have everything except for 0, negative 2, and positive 2, right? But I'm not going to write it that way. I'm going to write it as an interval notation. So those values, 0, negative 2, and positive 2, are the holes in my domain, right? If I start at negative infinity, which one of those do I encounter first? Negative 2. Why negative 2? Because it's the smallest number, right? We're starting from the smallest and working our way to the biggest. So the first number we'd encounter that's a hole in our domain is negative 2. So we'll go everything less than negative 2. And then we'll start at negative 2. What's the next hole in our domain? 0. And then we'll start at 0. And what's the next hole in our domain? 2. And then we'll start at 2 and cover everything else because we've passed all the holes. Is everybody okay with that? Really no more complicated than the previous one. It's longer, but like, whatever, Mr. Kulik, I just do it the same way, right? I just have more than 2 intervals. Whoop-de-dee-doo. I agree. That's the gist of it with the domain. Everybody feel comfortable doing that? Pretty easy. In general, all of these key features are pretty easy to do the singletons for. What's going to be difficult is keeping straight what to do between the things. Yes, sir. Sure. Next thing up, we're going to talk about discontinuities. And there are 3 types of discontinuities. There are infinite discontinuities. Those are really just vertical asymptotes. We'll use those 2 terms interchangeably. You can have a whole or a removable discontinuity. Again, we can use those 2 terms interchangeably. And then a jump discontinuity. So to just illustrate what we mean by these, I'm going to just kind of sketch a little picture here that has each of these going on. So this is just a little example. So our infinite discontinuity looks like a vertical asymptote. So that's a vertical line the graph approaches but never crosses. Our whole is just like a single point that's missing from the graph. And our jump discontinuity is where the graph ends at one spot but then picks up and starts again at a new spot. The good news is only the first 2 can happen in a rational function. You can't get a jump discontinuity for anything we're going to do. But I figured I should say, you know, if we're talking about discontinuities, those are the 3 types. We just don't have to worry about the 3rd type for what we're doing today. Everybody feel okay, comfortable, like kind of what I mean by these? I think a picture says a lot there rather than going and doing a words definition. It's one of those like you know it when you see it. All right. So to find vertical asymptotes. So to find the vertical asymptotes, we're going to set the reduced denominator equal to 0 to solve. And those solutions are just going to be our equations for the vertical asymptotes. So like x equals 2, x equals 5, whatever. Those are the equations for the vertical asymptotes. Because remember, vertical line starts x equals, right? To find the removable discontinuities, we're going to set any factors completely reduced from the denominator equal to 0 and solve. The solutions are going to give the x coordinates for our removable discontinuities, right? Because then the removable discontinuity is a point. To get the y coordinate to go along with it, we're going to plug those solutions into the reduced version of the rational function and evaluate, and that'll give us the corresponding y coordinate to go with that. So let's look at some examples of doing this. Yes? Okay. First things first. Are we always going to have a vertical asymptote? No, right? So not every polynomial equation has a real solution. If you have imaginary solution, those don't count as asymptotes, so you don't necessarily get any asymptotes, right? Could you have one asymptote? Could you have two?
Yeah.
Could you have three?
Sure.
Yeah. Can you have infinitely many?
Sure.
Well, no, but finitely many as you want, you can get, right? Because a polynomial can have n solutions. Okay. Everybody's good? But notice that each of these procedures now talk about reducing the polynomial or reducing the rational function. Let's look at how we do that at the same time as going and doing some examples. Okay, so I have three examples here, x plus 2. The first one is x plus 2 over x squared plus 6x plus 5. So in both looking for holes or vertical asymptotes, the first step is going to be to try to reduce our polynomial, or sorry, our rational function. Our first step in reducing is to factor the numerator and denominator. So if I look at the numerator, x plus 2, that's a degree 1 leading coefficient 1. There's no reduce or no factoring that could possibly happen with that. X squared plus 6x plus 5, that's possibly factorable, right? So what we're doing is we're going to look for two things that multiply to give us the 5 and add to give us a 6. Those two numbers would be not 3 and 2. 5 and 1, right? We have to multiply to get us 5 and add to give us 6, not the other way around. Now, question, can I reduce like that? Just cross those x's out. No is the answer. If I see anyone doing any reducing like this, there will be no partial credit on those questions in which you do that sort of reducing. As a fair warning to you right now. To reduce a rational function, it's either the entire factor or nothing. You can't just reduce part of an addition or subtraction problem. It has to be the entire addition or subtraction piece or nothing at all. So notice the x plus 2 is different from the x plus 1 and the x plus 5, correct? None of those are identical. No reducing to do here. Since there's no reducing, can we have a removable discontinuity? No, because it requires reducing to happen. So for the vertical asymptotes, then I'm just going to set these factors equal to 0. and I get two vertical asymptotes here. One of them at x equals -1 and the other is at x equals -5. Everybody feel good there? Let's do the next one. We start the same way. We want to start by factoring. Obviously, x plus 2 still doesn't factor. X squared plus 5x plus 6. How does that factor? There you go. Now we're ready. X plus 3 and x plus 2. Now notice here, the x plus 2, I have an identical x plus 2 in the bottom and the top, right? So those can reduce. What does this reduce down to? Doesn't reduce down to x plus 3. It's 1 over x plus 3. Everybody caught that? Don't forget the 1 overs. So I notice here that the x plus 2 is completely reduced from the denominator, right? I start with an x plus 2 down there, and now I don't have one. So that will cause our removal of discontinuity. So I'll take that x plus 2, set it equal to 0. And that gives me the x coordinate of my removable discontinuity is at -2. To find its y coordinate then, I'll take that -2 and plug it into my reduced version. That gives me 1. So my removable discontinuity is the point -2, 1. That's where the hole in my graph would be. That's the location where there is no point there. We just draw it with an open circle on our graph like I did in the previous picture above. Everybody's cool? Now for vertical asymptotes in my reduced my reduced rational function, I still have the x plus 3 down there. So I still set that equal to 0 and solve, and that gives me a vertical asymptote at x equals -3. So I can have removable discontinuities and vertical asymptotes at the same time. That's fine. Everybody feel good? Okay. Our last example, x plus 2 over x squared plus 4x plus 2. Again, we'll start the same way. Obviously, nothing to do with that x plus 2. How does x squared plus 4x plus 4 factor? Good. X plus 2 and x plus 2. So again, I notice, hey, I have an x plus 2. I can reduce one copy from the top with one copy on the bottom. That's going to leave me with 1 over x plus 2. Do I get a removable discontinuity here? I reduce something. Is it cause a removal discontinuity though? No. Why not? Because I still have x plus 2 in the denominator. It hasn't been completely reduced. I still have a copy of it left. Everybody's okay there? This is the trickiest situation. Yes, Max?
So when you factor things out, as long as there isn't like x plus 2 in there, then you have a hole. If it's, not like the first one, you can cross off 1. If you have like x plus 4 or x plus 5, it'll still be a hole in your graph, but as long as it's just x plus 2, it's not.
So if you reduce it completely, like we did up here, where there's no more x plus 2, if you cross a copy out, that makes a hole. If we have down here where we crossed it out, but we still have it, no hole. It's just an asymptote then. So notice we still do have an asymptote at x equals -2. And a good check is that the x coordinate for your hole can't be the same as the location of an asymptote. Those can't share the same x value. So if you catch a situation where you have a hole at -2 something and a vertical asymptote at -2, you've done something wrong. Those two things can't exist at the same x location. Does that feel okay? Okay. Next up is x-intercepts. So to find the x-intercepts, we're going to set the reduced numerator equal to 0 and solve. Those solutions give us the x-coordinates for the x-intercepts. The y-coordinate is just always going to be 0. Okay. So the first thing we want to do, because we're talking about reduced numerators, to check to see if we can do any reducing. So I want to start by factoring. Again, obviously the x minus 3 isn't going to factor, so that just is going to stay the same. How does x squared plus 3x plus 2 factor? That would multiply to give us x squared plus 5x plus 6. 2 and 1 are the numbers you need. Multiply to give you 2, add to give you 3. Is there any reducing that can happen? Nope. So I'm just going to take that numerator and set the factors each equal to 0. And I'm going to be very careful here when I'm doing this, is I'm going to write my x-intercepts always as points rather than x equals -2 and x equals -1. I'm choosing to do that because I also potentially have vertical asymptotes in the same problem, which are going to be written as x equals some number. What I desperately want to do is not confuse myself between my x-intercepts and my vertical asymptotes. So I'm always going to write my x-intercept as a point so that I don't confuse it with a vertical asymptote that's a line. So far, so good? All right. 5, maybe do one more, I guess. So I have x squared minus x minus 6 over x squared minus 9. First step is to factor. How does x squared minus x minus 6 factor? X minus 3 and then x plus 2. And x squared minus 9. Good. Do we see anything to reduce? Okay, so I'm only looking at the reduced version, so I'm going to set that x plus 2 equal to 0 and solve. So there we go. What's the x minus 3 going to do? That's a removable discontinuity that we would have taken care of at a different, but it's not an x-intercept. Everybody cool? We see that?
Only the stuff on top, in this particular section can become x-intercept.
Correct. It's always numerator and only reduced numerator. So you got to check to see if you can reduce first. Because if you would have taken the x minus 3 and tried to create an x-intercept out of that, it wouldn't have worked, you know, like that's wrong. That's actually where a hole is. All right, everybody feel okay for x-intercepts? Yes. So to find a y-intercept, we just plug x equals 0 into the reduced rational function and evaluate. The result gives us the y-coordinate. The x-coordinate is always just 0. So this is the easiest one typically. Most students don't have any problem here. So for my y-intercept, we're just going to plug 0 in for x. So I got -2. So my y-intercept is at like 0, -2. Everybody's cool? No big deal, right? Easy peasy. So to find the horizontal asymptote or slant asymptote, every rational function will have one or the other. We'll never have both. We need to compare the degree of the numerator with the degree of the denominator. That's going to generate 3 cases for us, because we can either have the degree of the numerator, let's start with less than, the degree of the denominator. In that case, we always have a horizontal asymptote, and it's always y equals 0. The next possibility is that the degrees are equal. In that case, we also get a horizontal asymptote, but here it's not going to be y equals 0. It's going to be the leading coefficient of the numerator over the leading coefficient of the denominator. And our last case is where the degree of the numerator is greater than the degree of the denominator. So that's going to have a slant asymptote. And the equation for that slant asymptote is going to be the equation for a line, a y equals like mx plus b, where that mx plus b is going to be the quotient of the numerator divided by the denominator. So you're going to have to do polynomial division there to get that equation. So either that means long division or synthetic division, depending on what that denominator looks like. Everybody feels okay? So I'll do a couple examples here. So I have 3 examples here. So the first example is y equals 3 over x plus 1. We want to start by figuring out the degree for the numerator and the degree for the denominator. What's the degree for the numerator? What's the degree of a constant? 0 is correct. What's the degree of the denominator? It's not 0. It's 1 because it has an x to the first there. Okay, since 0 is less than 1, we're in case 1. So we just have a horizontal asymptote at y equals 0. Does everybody feel good there? So for number B, letter B, we have 2x squared plus 5 over 6x squared minus x plus 5. The degree of the numerator is? Degree of the denominator is. So those are equal. That puts us in case 2. So again, I'm going to have a horizontal asymptote where it's the leading coefficient of the numerator over the leading coefficient of the denominator, or just y equals 1/3 if we reduce that down. So far, so good? Okay. If I look at our last example, the degree of the numerator is? Degree of the denominator is? So this is clearly case 3, so I'm going to get a slant asymptote. Now the equation for that slant asymptote is going to come from the division of the numerator by the denominator. Since the denominator is degree 1 and leading coefficient 1, I can use synthetic division to do this, which would be my preference. If you give me the choice, I would much rather do synthetic division than long division. So remember, the numbers at the bottom are reading from right to left, remainder, constant, x coefficient, x squared coefficient, and so on and so forth. The part that's our quotient, though, is the non-remainder part. Not for the slant asymptote. The slant asymptote is always just going to be the quotient. The remainder doesn't tell me anything about the slant asymptote. Colby. I said x plus 3 equal to 0 and solved. You're talking about this negative 3? Yes. So you always set the denominator equal to 0 and solve. And that'll give you the what number to put out there. You guys cool? So far, so good? Okay. Sorry, I'm kind of ripping through this. We just had a lot to do, and we have 15 less minutes today than we did the other days. The last thing to talk about are now end behaviors. So every rational function has 2k plus 2 n behaviors, where k is the number of vertical asymptotes. So how many n behaviors would I have if I had 3 vertical asymptotes? I'd have 8, right? 2 times 3 plus 2. 2 times 3 is 6, plus 2 more is 8. Everybody's okay with that? All right. I'm going to start with a graph to n behaviors example, and then we'll do a equation to n behaviors example after that. Sound okay to you guys? So I'm going to just kind of draw in some asymptotes. So I just kind of made up a graph here to practice doing n behaviors. So this graph had 3 vertical asymptotes, so it should have 8 n behaviors. Those 8 n behaviors are going to correspond to the heads of each of these arrows on our graph. Is everybody okay with what you're looking at? So remember from last chapter when we talked about n behaviors, they're always going to look like this, right? That's our general format for our n behavior. The limit as x approaches something of f of x equals something. Well, this first blank, the x approaches, is kind of like an x, and this, where the limit equals, is kind of like a y. So the easiest way to think about these is to look at each one of these n behaviors like or each of these arrows, and think about it like a point. So I'm going to look at this arrow to start. Now that arrow's pointing to the left, correct? So its x value is like -infinity. But that arrow is like flat following that x-axis, so its y-coordinate is like y equals 0. So my first n behavior, I would say, the limit as x approaches -infinity of f of x is equal to 0. Is everybody okay with what we're doing? Like, just think about each arrowhead as a point, and then I'm just filling the X and Y into the format. All right, let's look at this arrowhead now. That arrowhead is located at -4, but it's pointing down. So it's like the point -4, -infinity. Since the arrow is pointing up and down, it's the Y that's going to be positive or negative infinity. So we'll say the limit as x approaches -4 of f of x equals -infinity. If I go and I look at 3, that is also located at -4, but this time it's pointing up, so it's like -4 positive infinity. Is everybody feeling okay with what I'm doing? Seemed like we had problems with end behaviors on the last test, so I'm just trying to be real careful and give a extremely detailed example on what to do here. Now, there is a little bit of a problem with what we've just done in these last 2 steps. Does anybody see the problem, the thing that we don't like as mathematicians? It's not the 0. Both those limits are as x goes to -4, but they're going to different places, right? So we need to clean this up a little bit, because that limit number 2 is talking about the left-hand side of -4, and limit number 3 is talking about the right-hand side of -4. So we need to denote that somehow, that one limit is talking about the left-hand side and the other is talking about the right-hand side. The way we're going to do that is use a superscript on the number 4. So for left, we're going to put a negative in the superscript. And for right, we're going to put a positive in the superscript. Is everybody okay with that? So that's going to be how we're going to communicate which side of -4 we're talking about. Cool? Okay. So that cleans up that issue. Let's go on to number 4. So that point looks like it's at -1, but it's the left side of -1, and it's pointing down, so -infinity. Is everybody okay with that? So write our next limit. As x approaches -1 from the left of f of x equals -infinity.
What about the 0? Unlike the first one. Because that's like coming up under
We don't need to do that, because it's okay for a function to go to the same y value. What's not okay is for the same x to go to 2 different y values. So we're only worried about the left and right from the x's. You can think about the y's as above and belows, but we don't need to denote that, because there's no conflict in having a function where you have 2 x's that go to the same y value. That's okay. Does that make sense?
Yeah.
So that's a nice observation. You can certainly think about that. And if you take like a calculus course, there's certainly problems where that's a helpful observation to make, and you'd want to talk about that, but not here. Feel okay? All right. Why don't you guys try to write in 5 and 6 on your own? I'll give you guys like a minute here of a head start to try to write in your own 5 and 6 before I start writing in the answer. Or at least think about it in your head, or whatever you want to do, but take a moment here and try to do 5 and 6. I'll give you guys like a minute head start, and I'll start writing in my answer, and we can check. So for 5, I got the limit as x approaches -1 from the right of f of x equals positive infinity. And for 6, I have the limit as x approaches +2 from the left of f of x equals positive infinity. 7 then will be the limit as x approaches +2 from the right. Also goes to positive infinity. And the last one, if we look at that point, this time the arrow, instead of pointing up and down, is pointing left and right. Since it's pointing to the right, it's the x value that's going to positive infinity. And because the arrow is flat on y equals 3, the y value is 3. So we'd have the limit as x approaches positive infinity of f of x is equal to 3. Nobody have like a seizure with this light flashing on and off. I'm sure that Matthew and Vincent are like going nuts back there as they're sitting in the flash zone. All right, so a couple of observations here real quick. So these limits here, those are the end behaviors that are a result of the vertical asymptotes, right? Notice each vertical asymptote gets 2 end behaviors, one for its left side and one for its right side. The other 2 end behaviors are a result, the other 2 end behaviors are end behaviors that every function is going to have. Every function is going to have an end behavior as x goes to -infinity and as x goes to positive infinity. That's there always, whether you have vertical asymptotes or not. Those extra ones in the middle where x approaches a number from the left and right, those are the result of the vertical asymptotes. Does everybody feel okay about what we're looking at? Did that help with our end behavior writing? I hope a big long example that was pretty detailed. All right, what if we want to go from equation to end behaviors? So before I start, I need 2 things before I get going. I need to have the vertical asymptote and the horizontal or slant asymptote. Everybody's good with that? Now, clearly this can't reduce, so I don't have to worry about reducing anything. So to get that vertical asymptote, we'll just set the denominator equal to 0. And to get our horizontal or slant asymptote, I notice that this is degree 1 on top and degree 1 on bottom. So my horizontal asymptote is going to be y equals the leading coefficient of the top over the leading coefficient of the bottom. Everybody feel good so far? So right from here, I know I'm going to have 4 end behaviors. And I can write the x parts of all 4 of those end behaviors right away. So the limit as x approaches -infinity, the limit as we approach 2 from the left, the limit as we approach 2 from the right, and then the limit as we go to positive infinity. Now, the infinity ones, the y's, are very easy to do because those y values are always going to be the same as that horizontal asymptote. So I can just fill those in. Now, the vertical asymptotes I know are either going to be positive infinity or negative infinity. What I really just need to do is check which one it's going to be. So the way I would check this without graphing it on my calculator, although that's not unreasonable for you to just do it and look at the picture and do it the same way you did the previous one. I want to show you how you could do it by hand also. So what I want to do is I want to look at x approaches 2 from the left. So I'm going to look at x equals 1.9 and then x equals 1.99, and see if the y value is going up or going down as I get closer to 2. Can you guys just give me 1 minute to finish this particular example? Okay, I'm sorry, I don't ask you to do this very often, but I appreciate your patience. We're almost there. So what's happening here? Are we going up or are we going down? We're going down, so that's going to negative infinity. To do the other side, I'll just do the same idea, except I'll use 2.1 and then 2.01 and look at what's happening with the y's, right? So I'm going to get there 31 and then 301. So here we're going up, so that should be positive infinity. And there I'm done. For the virtual day, you guys will have a Delta Math assignment doing this kind of stuff. Okay? Good luck. Bye. Thank you for your patience. I appreciate the extra minute you guys were willing to grant me.